Good afternoon, my name is Yulia Khabibullina. I'm Research Fellow of the Department of Geochemistry of Faculty of Geology, Moscow, Lomonosov, Moscow State University. My today's lecture is going to be on usage of state-of-the-art analyzers for prospecting of porphyry copper deposits. You're welcome. Here is a brief overview of what my presentation is going to be about. I'll start with a section on X-ray fluorescence. It's not the only portable analytical method being used in exploration nowadays, but I'm going to focus on it mostly. I'm going to speak about how it actually works, what it can and cannot do, different operation modes, its advantages and disadvantages, and since its radiation is ionizing, I must refer to radiation safety when using such analyzers. The second section will address the technology of geochemical prospecting of porphyry copper. I'll show the commonly accepted model of a porphyry copper system by tool. I'll say a few words about geology and mineralogy of the Bank area, which was the object of the presented case study. I'll discuss what we could expect from portable XRF in our situation, and finally, I'll show you what we did, how we interpreted the results of geochemical survey, and how we assessed the area prospectivity. Let's start with the principal physics of X-ray fluorescence. The most common source of X-rays in portable analyzers is in X-ray tubes. It produces radiation that interacts with inner electrons of atoms, so that inner electron is ejected. You can see it here in the picture. Because of the vacancy in the inner electron shell, atom becomes energetically unstable. To bring it back to a stable state, an outer electron fills the vacancy, and the energy difference between two states is emitted as a secondary X-ray photon. And this secondary radiation is being received by a detector and displayed in the spectrum. Each electron transition in each specific element has its individual energy value, so by the energy of photon, we can decide on the atom of which element emitted that photon. That is why secondary radiation is also called characteristic radiation. And by the intensity of that secondary radiation, we can say how many atoms of that kind there are in the matter being analyzed. For heavy elements, several electron transitions with various energy losses are possible, so in the spectrum we can see a series of energetic peaks. Here spectral lines are given in the Ziegler notation system, and the names consist of the symbol of the chemical element, the symbol of the shell that held a vacancy, and a Greek letter denoting the particular line in the series. So what elements can be excited by the modern portable, or as they are sometimes referred to as handheld analyzers? As you can see, we can start with the magnesium, given that we use specific technologies. Majority of the elements can be analyzed in most cases, although with limitation on content and matrix of a sample. What limits of detection are promised? Well, here I'm given a table for Olympus and Vanity spectrometer, but other manufacturers advertise pretty much the same lots. For lighter elements, we should expect limits of 3,450 ppm, and for other elements, detection limits are below 5 to 10 ppm. So far, so good, isn't it? But as any advertisement, there is a fine print in the bottom. Let's take a closer look at it. Quote unquote, detection limits are a function of testing time, sample matrix, and presence of interfering elements. So, the length of the testing time, the better the reliability of a measurement. Optimal time is from 50 seconds on. There are several matrix effects. One of them is the spectral interference. As you can see in the table A, some spectral lines have quite close energy values, which means detectors with a lower resolution will not distinguish between them. For example, in the samples with a high concentration of galena and thereby high content of lead, Spectrometers would show arsenic, even though there might not be any considerable amount of it. Absorption and enhancement effects arise from inner interaction of fluorescent radiation with the atoms of a sample before it reaches the detector. Therefore, spectral line intensity may be increased or reduced. Specimen-dependent effects include particle size, surface texture, and heterogeneity effects. These factors affect penetration of X-ray tube radiation, excitation of the atoms, and final spectrum. They are mostly dealt with by appropriate specimen preparation. Heterogeneity of the specimen imposes constraints on preferable operation modes. For instance, when we use spectrometers in so-called point-and-shoot mode, we shouldn't expect quantitative analysis unless media is naturally fine-grained and homogeneous. Mole heap mode, picture B, allows to estimate element ratios, abundances, and sample ranking, but bias in analysis can be caused by moisture and airspace between grains. If hard media is fragmented and melt, like in the picture you see, analysis quality improves. And only with lab-type preparation, when material is dried, sieved, and homogenized, we can expect quantitative analysis within the instrument's performance limits. In some advertising booklets, we can find a picture of an operator running the analysis through a plastic bag. But it looks rather convenient, but one should consider that light element spectral lines will be attenuated by plastic. For example, this silicon K alpha line will be reduced by almost 40%, even when we use sample cups with mylar film of 6 microns thickness. On most instruments, there are different calibration for trace and major concentrations. So mode utilizes counter-normalization and is used for trace concentrations. Mining mode is the best approach for high concentrations and for quantification with fundamental parameters. Some instruments are like a hybrid mode, which provides some quantitative data over a larger range. If both trace and major level concentrations are desired, a change of mode is needed without moving the analyzer between two measurements. This is longer, but it improves accuracy. And finally, we can get the most of PXRF when we use an empirical little calibration using certified reference materials, CRFs. Let's sum up advantages, and I wouldn't call it disadvantages, but limitations of PXRF. It's a non-destructive method to analyze various samples from solids to liquids in versatile size, shape, and conditions. It requires little to no sample preparation. It is fast, convenient, and under certain conditions, sensitive, precise, and accurate. Unlike most of the element analysis techniques, it allows a wide concentration range detection, from 1 ppm to 100%. It is a cost-saving alternative to classical laboratory analysis and especially suitable for real-time decision-making in remote and harsh field conditions. Limitations are light ounces analysis, matrix effects, and the need for chemically and physically matching theorems. It cannot substitute laboratory analysis when dealing with precious metal prospecting and exploration. And talking about safety, in general, X-rays may kill, damage, and cause genetic change in biological tissue. This is the basis for X-ray health hazard. This hazard is insidious because X-rays are invisible and otherwise undetected by human senses. But let's take a look at the actual doses that can be received by operator when operating portable spectrometers. So the highest shallow or skin dose is on the contact of the skin with the beam. And the distance of 5 centimeters, it is already 10 to 50 times lower. Maximal deep dose that can be received is 20 times times less than the radiation standard according to the Russian standard RNBM 99. A competing technology for portable elemental analysis is LIPS, which stands for Laser-Induced Breakdown Spectroscopy. This technology uses a short laser pulse to create a microplasma on the sample surface. It offers a broad elemental coverage, including lighter elements. It is almost non-destructive, super fast, and requires little to no sample preparation. But since it's extremely sensitive to matrix effects, it is essential to use matrix match theorems. It did not break through as PXRF, but it provides complementary applications for lighter elements and through its remote detection capabilities. SciAps sells both XRF and LIPS in one box, supporting the idea of complementarity. And here is the slide to support sensitivity for light elements. Okay, let's now move on to an application of PXRF for prospecting of porphyry copper deposits. To begin with, I shall mention that porphyry copper deposits presently supply nearly 3/4 of the world copper, half the molybdenum, about 1/5 of gold, most of rhenium, and minor amounts of other elements. The most notable high-grade deposits are located in the Circum-Pacific zone. The clusters of the porphyry copper systems are associated with the active subduction zones, defining linear belts. Depending on the formation conditions and erosion level, the system may host various types of mineralization: porphyry deposits centered on the intrusion, skarn, carbonate, replacement deposits, and subepithermal deposits in peripheral locations, and superjacent high and intermediate sulfidation deposits above. The Bayanka trade, the object of this case study, is located at the very end of the world in the Chukchi Peninsula. And this region is famous not only due to its ex-governor Roman Abramovich, but for the largest porphyry copper resources in Russia as well. Geology-wise, the region comprises the Upper Jurassic volcanic sequence intruded by bodies of various composition and age. Ore mineralization here is related to early Cretaceous intrusion of a large subalkaline plutone, accompanied by numerous stocks and dikes of porphyry quartz monzonite and porphyry cyanide. The Pishanka deposit of the Bayanka trend is considered the largest porphyry copper gold molybdenum deposit in Russia. Valent disseminated porphyry mineralization consists of pyrite, chalcopyrite, bornite, and molybdenite. Subepithermal mineralization is presented here with late gold-bearing galena, sphalerite, fluorite, and calcite veins. Besides, we found amatite and hessite here, which are believed to be the remains of the intermediate sulfidation stage. This type has been developed sporadically at Pishanka. 7 years ago, we participated in the prospecting project in the Bayanka area and got 2 nitrogen analyzers. And the question was, given all this technical specification, will the spectrometers be sensitive and accurate enough to detect soil anomalies of the following elements? There are typical ore elements in the first group, and elements associated with alteration of rocks in the second group. We ran pre-filled quality control assessment and tested 24 CRMs with a matrix matching soil and mineralization of porphyry copper environment. Random and systematic errors turned out to be low, and if there was a systematic bias, we offered correction factors. Also, we had a chance to compare PXRF results with those of ICP for almost 3,000 soil samples from the territory of interest. They came in close agreement. The Pearson correlation coefficient ranged from 0.7 to almost 1. The undertaken study allowed us to specify limits of detection in given background soil samples. And here we can compare specified lots with geochemical background parameters of soil. As you can see, nitrogen loads are sufficient enough to identify even weak anomalies
of most of the elements of interest. Moreover, the quality of analysis meets or exceeds one of the traditional semi-quantitative spectral analysis. And this is what we did in the field. Geochemical prospection begins with collecting soil samples within a given grid. Then soil samples are dried, sieved, packed in reusable sample cups, and finally analyzed. We managed to run 160 analyses per 8-hour shift with one analyzer. By the end of the season, we were able to upload the results to this project and delineate anomalies in soils. Actually, this rate of analysis enables trenching and drilling in the same season based on newly obtained analytical data. And here are the maps of geochemical anomalies in soils. To identify the gold content, we had to opt to laboratory fire safe with AAS finish. Intensive anomalies of copper, molybdenum, lead, zinc, and other elements were revealed, and here's how we interpreted them. According to the correlation between elements concentration, there are two basic types of mineralization of the binary trend: porphyry copper type and gold silver with base metals epithermal type. We offered criteria to delineate prospective ore bodies by their corresponding anomalies in soils. Basically, we analyzed the structure of the geochemical field and marked its core, transit, and outer zones, where core zones correspond to ore bodies. When talking about prospectivity of objects in such distant location in the Chukotka Peninsula, one should consider an assessment of ore metal grade. And here's how we tried and assessed ore metal grade by metal content in soils. First of all, we could compare copper and other elements concentrations in surface ore and in the soil above. For porphyry copper mineralization, we can observe copper loss with coefficients lower than 1 during the formation of secondary halos. The loss is not typical only for high gradient slope because of the fast renewal of secondary halos as a result of erosion. As for associated elements, their redistribution is not sufficient. For gold silver mineralization, we estimated gold enrichment here. Gold enrichment of secondary halos up to the formation of a tubular placer at the foot of the slope. This happens due to releasing of gold from pores and slowing of its migration in the low gradient elementary landscape. We know that primary sulfate ore is a target for oxidation. How can it affect our estimation of ore grade? Let's take a look. In the presence of water and oxygen, pyrite is to be oxidized producing sulfuric acid. In acid environment, chalcopyrite is being dissolved, the third equation. And the copper migrates in solution downward to the redox boundary. There it reacts with reduced sulfur to precipitate as a secondary sulfide. If migration of copper is slow, then copper precipitates as well carbonates, malachite, and azurite. I'd like to stress that dissolution of copper tends to leaching of that metal, but the redox boundary, secondary sulfides, contains 2 times more copper compared to primary chalcopyrite. So this zone enrichment takes place. It will be clear in the next slide. As you can see, just under the surface, there is a low-grade interval called leaching zone. Leached copper migrates from here downward and forms secondary high-grade sulfides. Below this enrichment zone, there is an interval of hypergeneralization. So this surface interval is a substrate for secondary halos. In some cases, copper content in this interval 3 times lower than in the primary ore. But in other cases, Surface interval includes enrichment zone, and then average copper concentration may exceed its concentration in hydrogen ore. But what's the average? We found out that oxidation was spread sporadically, but leaching could lead to loss of 50% of copper, while the formation of secondary sulfides could end up with 2 to 5-fold enrichment. It means that we need an additional coefficient to adjust to such drastic elementary distribution. And here are the coefficients to be applied to copper concentration in soils to estimate its concentration in the primary ore. As you can see, secondary halos of copper are 2 times weakened on average. Secondary halos of gold are weakened by 25%. And here's my last slide, summarizing technology of geochemical prospecting of porphyry copper with the use of portable XRF. I'll repeat it briefly. We collect samples within an optimal grid of 200 by 100 meters. After simple sample preparation comprised of drying and sieving of the material, we run the XRF. Based on obtaining analytical results, we delineate geochemical anomalies in soils and identify geochemical structures corresponding to prospective ore bodies. With the use of 2 coefficients, we assess concentration of metal in primary ore as corresponding to its content in the soil. There is one more step of erosion assessment according to vertical geochemical zonation of porphyry copper systems, but it can be topic of a separate lecture. And the final result of geochemical prospecting is an estimation of undiscovered resources and assessment of their prospectivity. Well, I guess that's it. Thank you for your attention.